Hey everyone, welcome. Today we're tackling Leetcode problem 3027. Find the number of ways to place people to. This is a really interesting geometry problem on a 2D plane. It looks a bit tricky, but we'll break it down into simple, understandable steps. Let's get started. Okay, so here's the official problem statement. I'll give you the simple version. We're given a bunch of points on a graph, and our job is to pick two of them, Alice and Bob, to build a rectangular fence. The core idea is about forming a rectangle. We choose one person, Alice, to be the top left corner, and another person, Bob, to be the bottom right. For this to work, Alice's x-coordinate has to be smaller than Bob's, and her y-coordinate has to be larger than Bob's. Simple enough, right? But here's the catch, and it's a big one. Once we've picked Alice and Bob and imagined our rectangle, we have to make sure nobody else is inside that rectangle, or even sitting on its edges. It has to be an empty space, just for Alice and Bob. This is where the part 2 of the problem title comes in. The problem states that Alice does not become sad. This is a bit of a story, but what it really means is that for a chosen pair, no other point can hijack their corner roles. For example, if we pick Alice and Bob, there can't be another point directly below Alice that could also form a valid fence with Bob. The chosen corners must be unambiguous. Okay, let's think about our first approach. The most straightforward idea is to just check every single possible pair of points. Let's call one point Alice and another one Bob. But how do we do this efficiently? A great first step in many geometry problems is to sort the points. If we sort them by their x-coordinate, we can pick a point for Alice, and then we only need to look at points after it for Bob. This automatically handles the Alice is to the left of Bob rule. Just checking pairs is still too slow. We need an optimization. Let's fix our Alice. Now we'll scan through all the points to her right, looking for a good Bob. A point is a potential Bob if it's below Alice. As we find these potential Bobs, let's keep track of the highest y-coordinate we've seen among them so far. Let's call this maxY. Now, for the next potential Bob we find, its y-coordinate must be lower than our current maxY. If it's not, it means our previous best Bob would be inside this new taller fence, which isn't allowed. This little trick is the key to avoiding a third loop. And here's the code that puts that idea into practice. Notice the sorting at the beginning. We sort by the x-coordinate, and for ties we sort by the y-coordinate in descending order. Then we have our two loops. The outer one picks Alice, and the inner one looks for Bob. That ymax variable is our optimization, keeping track of the highest valid y-coordinate we've seen for the current Alice. So how efficient is this? The sorting part is n log n, praisens, but the main work happens in the nested loops, which gives us a time complexity of big O of n squared. Prain. This is pretty good. For space, it's very efficient. Depending on the sorting algorithm used, it's either constant or linear space. Alright, let's explore a more advanced technique. Whenever a problem asks you to count things inside rectangles, a powerful tool to consider is a 2D prefix sum. The main challenge here is that the coordinates can be huge, up to 1 billion. We can't create a billion by billion grid. So the first step is a trick called discretization, or coordinate compression. Here's how discretization works. We gather up all the unique x-coordinates and all the unique y-coordinates from our points. Then we sort them. The first unique x-coordinate gets mapped to index 0, the second to index 1, and so on. We do the same for the y-coordinates. Now instead of dealing with numbers like 50999, we're working with small indices like 2 and 3. This makes creating a grid manageable. Once we have our compressed grid, we build a 2D prefix sum array on it. Think of it like a running total, but in 2 dimensions. Each cell in this prefix sum grid tells us the total number of points in the rectangle, from the top left corner of the grid, all the way to that cell. The magic is that with this pre-calculated data, we can find the number of points in any rectangle on our grid, with just 4 lookups and a little bit of arithmetic. It's an incredibly fast way to query rectangular regions. This code looks more involved, but it follows our plan exactly. First, it performs discretization, creating maps for the x and y coordinates. Then, it builds the 2D prefix sum grid. The query function is where the magic happens, calculating the number of points in a rectangle, in constant time. Finally, it iterates through all pairs, just like before, but this time it uses the super-fast query to check if the space between Alice and Bob is empty. For this approach, the time complexity is also big O of n squared. Even though the query is fast, we still have to build the prefix sum grid and check all the pairs, which takes n squared time. The main difference is the space complexity. We need to store the grid and the prefix sum array, so the space required is also big O of n squared, which is a bit more than our first approach. So let's wrap up. We saw two great ways to solve this. The first approach used sorting and a clever trick to check for empty rectangles efficiently, and it was very light on memory. The second approach introduced a more general purpose and powerful technique, coordinate compression, combined with 2D prefix sums. Both methods end up with the same n² time complexity, which is a great lesson in how different algorithmic ideas can lead to similar performance. Hope that breakdown made sense. If it helped you understand the problem better, please hit that like button, and maybe subscribe for more explanations like this. If you have any questions or a different way of solving it, drop a comment below. And hey, if you're feeling extra generous, there's always the Boba Fund. Keep coding, and I'll see you in the next video.